Hello everyone and welcome to this Geographic Information Systems course, and today we are going to discuss GIS analysis part 5, and in this as we have been discussing earlier about the neighborhood operations, and before that also the buffering and other things, and now in this one we are going to discuss this connectivity operations, and which are again very important, especially related with the various analysis for finding suitability for certain projects, and also from network point of view also, because that is another very good application of GIS in network related things. So, we will be going through this discussion about the connectivity operations. Basically here also like in interpolations the estimations are done. So, here connectivity operations estimate values by accumulating them over the area that is being traversed, and this is if I give an example here, that like if I have to climb a mountain, then initially I might be going at a little higher speed, but when suppose I have spent 1 hour time, now it will take more time to travel to the same distance. So, that the tiredness is getting accumulated. Similarly, in a plain area, if I walk for first an hour, then I may complete 5 kilometers, but in next hour I may complete 4 kilometer, and likewise my traveling or traverse reduces because the tiredness get accumulated. In case of like pollutants and other studies where dispersion occurs, so it is a reverse way, but again it can also be estimated using such operations in GIS. We will see further details on this with the examples also. So, in order to calculate this connectivity function, what are the requirements, what are the inputs? So, first specify the manner in which the spatial elements are interconnected, because this is based on the connectivity, and therefore, this interconnected information is very much required among the spatial objects or spatial elements. And second thing, that how things move, what are the constraint possibilities, that means the rules, and that will control the movement which is allowed along the spatial elements. So, suppose there is a pipeline or a river system, a stream, or maybe a road or a power line. So, what are the possibilities and what are the constraints that we have to also provide, because recall the initial discussion on GIS. GIS is providing software tools, various software tools. It is up to us to utilize them judiciously and very efficiently. Though the tools are, most of the tools which we can imagine are available nowadays with good GIS softwares, but only it is our capabilities, how much we can exploit. So, these rules or this understanding about that particular phenomena is very much required, and of course, third one is the unit of measurement. This we have to always take care while doing such calculations or estimations in GIS. So, connectivity functions can be grouped or can be divided into various sub functions. The first one is the contiguity, and we will see details about these functions little later. Then proximity, and the proximity part we have already discussed, like buffering or buffer zones, creating buffer zones. So, that is it is directly connected with a spatial object, a point along around which we create a circle. So, that is proximity, directly connected. Similarly, for polyline and polygon, and this proximity functions also comes the Thyssen polygon, which we have discussed while discussing interpolation techniques. And so, that is also a proximity function under this connectivity function, and a nearest feature identification, and that we also put in this proximity functions. And then the third sub function of connectivity is the network functions, which are very, very important, and they all come under this category of network functions. And then we are having spread functions. I will be showing some examples how this spread function can be exploited for various applications related with hydrology or planning of certain reservoir or even for groundwater. So, this spread function I will be also dealing in a demonstration, which will be the next after this lecture. So, and the last sub function under this connectivity functions is called the seek functions. Seek functions is based on generally on the surface hydrologic modeling, and when we will discuss in detail about the derivatives of digital elevation models, then at that moment we will be discussing also the surface hydrologic modeling, and in that we will be using this seek functions also. So, let us start with first contiguity. The contiguity basically measures characterized spatial units that are connected. So, because it's overall is a connectivity function, so things have to be connected, then only such measurements or estimations can be performed. A group of spatial units, those may be point, line, polygon, and that have one or more common characteristics. Now, common characteristics is another essential requirement and constitute a unit form of forms a contiguous area. Now, common measures of contiguous area are the size of contiguous area and the shortest and longest straight line distance across the area. So, these conditions will come under this contiguity function. So, in this one what we are basically doing, we are estimating the connected areas that share a common characteristics. For example, we might be doing in suitability analysis, we might be determining a land units which will be used as a nature reserves. So, this is our requirements. This is what we want to extract from the or query from the system through this contiguity function. And what are the conditions? The condition that it should include forest, it should include reserves, it should also include swamps, under the condition that the minimum area. Now, further constraints are there, further rules we are putting by before the analysis, that the minimum area which is being looked for this natural reserves is 400 square kilometer with no section narrower than 10 kilometer. So many conditions have been put to the only requirement would be after these conditions that this information must be available within our GIS database. So, like including forests, rivers, swamps, this information can come from two layers, one is land use, another one is drainage network. And then we can have then this condition about the 400 square kilometer, that minimum area, and no section narrower than 10 kilometer. So, like for example, in this schematic what we are having, this is our input map and land cover map is there, in which we are also having our drainage lines and other connectivity things. So this there is a swamp, there is a forest, and this after this iteration through this contiguity function or after this estimation, this is what we get, that these are the areas which are satisfying all your conditions, that they are having they are having area larger than or equal to 400 square kilometer. These are not narrow, like here this is narrow, so that is why it has not been chosen. This is not falling equal or 400 or more than 400 square kilometers. So, therefore, this area has not been selected, and also it should include forest and including forest, rivers and swamps. So, in that way our output is the contiguous area like this. So, in this way several conditions, if our data is having or our layers are having those kind of information, then we can estimate or we can determine land units to be used as a natural reserves in this example. But similarly people for many, if I give the example for municipal corporations, they are many times they are looking for suitable sites for dumps, waste dumps, solid waste dumps. Now there will be some conditions because there are environmental constraints and so many things are there, and plus it should not be close to population, and many things are there. So if we put all those conditions to our database, if we are having all those details in our database, then we can really find out very good suitable sites for waste disposal sites or waste disposal. Similarly, we have been involved in such projects where this analysis was done to find out the suitable sites for this fly ash dumping, because there are these thermal power plants which use coal to heat the water, and that waste of that coal is the ash, fly ash, and that fly ash has to be dumped somewhere. So wherever it will be dumped, it will destroy the soil and also to some extent the groundwater. So now if we know that how we can minimize this, and we can also think that what would be the transportation cost and other things. So all these constraints, conditions and rules can be put to the GIS system, where we are having a very rich GIS database, and the most suitable sites can be identified, maybe then 2-3 scenarios, that this is the most suitable site, then next and then next, and then decision makers can make decisions. This is what the purpose of GIS is, to provide scenarios, different scenarios through our modeling, through our analysis, so that decision makers can take very appropriate decision. If GIS user himself is a decision maker, then of course one step will not be, there will be one less step, but in many cases decision makers are different people than GIS users. So no problem, we can develop 3-4 scenarios that this is the most suitable site, but if socially or economically it is not possible, then this is next, then this is next. So a simple function which is contiguity function under this connectivity function is so useful to solve various problems related with our real life in different domain, whether it is a waste disposal, in civil engineering or in earth sciences or in electrical engineering. In many scenarios these things can be used. Now we come to this proximity functions. Some sections of proximity functions we have already dealt. Nonetheless, the proximity basically involves the measurement, as you recall the buffering in our previous lecture, and unit can be distance in length generally, or travel distance in time, or other units might be there like dispersion of pollutants, concentration. Now in order to calculate proximity, what are the requirements? The requirement first is object, that will be always means spatial objects. For example, there might be roads, groundwater well, thematic units, land use, forest, anything basically. And then you require unit of measurement, because if buffering has to be created, then you have to provide whether it has to be in terms of distance or in terms of time or in terms of concentration. And then a function, basically algorithm or knowledge about that phenomena for which you are going to use this proximity function, and that to calculate proximity. That, for example, that might be a distance, but this is not always true. There might be some other functions also. And the third one, the area of interest should be specified, in which area you are going to do. If I am having a complete database, say of Uttarakhand, but I want to perform this analysis only for a small area, so I have to provide that information also. So it would be quicker and easier for me to create such scenarios. Now example where this buffering is done, some examples we have already discussed. So determination of buffering zones, buffer zones along groundwater exploration wells, that is also one possibility. Construction of Thyssen polygons, while discussing interpolations we have already discussed. Then determination of accessibility to drinking wells. In many scenarios, especially in villages, we have to do this analysis, that what is the distance the people have to travel to fetch the water from a well. So that we can also analyze. here the distance calculation. First the distance calculation. So, basic trigonometric function will be used here, the distance from a source pixel, because here it is not necessary that you would be performing only on vector data. So, it can be raster data to its horizontal vertical neighbors and the distance from the source pixel to its diagonal neighbors is square root of this 2, that is equal to 1.4 and 1421. Now, while discussing this spatial filtering and the concept of neighborhood operations, there we discussed this moving window or roving window. You recall this this is 3 by 3 moving window or roving window in case of even many functions like calculating slope, aspect and other things also. Anyway, so this is our input map, and there are two categories in our input map. So, you can say it is a binary one, that there is a source and this analysis being done for fetching water. So, the source of water is located here and rest are the areas are having no water. So, basically they have been given as unidentified or undefined. Now, this is the distance in pixels. So, what we have discussed here, a diagonal distance is calculated. So, beyond this for these diagonal distance from these 4 cells. So, if you go just vertically upward, then it will be 1, but if you go diagonally upward, then it is square root 2. Similarly, in downward, and as far you go, the distance increases from the source of water. So, when we use this, that the multiply with the pixel size, here is the resolution, the resolution of this spatial resolution of this input data. So, now we can get distance about from water source to the different cells. So, now we are having distance. So, if the central pixel is defined here, central pixel in our matrix, this roving or moving matrix, one of the neighbors is not, then apply filter iteratively. That means that we will move this filter or this matrix or roving window throughout the data, and then calculation will be done. The only problems in such scenarios comes when we use roving window or moving window, which is not shown in this schematic, is on the borders. So, one thick pixel on right side, one thick pixel on left side, same in the bottom and top, there will not be any calculations, because on beyond this you do not have the input data. Anyway, so that way you can find out what is the distance. Now, if you are having travel time information also, that from coming like this 56 meters to this place, how much time it will take by walking or by on cycle or some other mode, then the time can also be involved or can be estimated in such calculations. Now, we come to this proximity analysis. During buffering, I gave this example, but here again this is the red line which is shown here is the road, and now the buffer has been created on both sides of the road is the 60 meter. Suppose now there is a plan to widen this existing road which is going through a habitated area. Now, whose house or whose plots will get affected? Immediately, if you are having a layer which is showing the revenue records or the plots of individual houses, and if you overlay this buffer, then immediately you would know that whose houses or whose plot would be taken by this widening of this road. Similarly, you can do analysis like if a stream is flowing, now I want to calculate the flood plain area. If there is a flood, say maximum flood which I get, and generally hydrologists use the 100 years time period. So, how much area would get inundated? That too can be analyzed using this proximity analysis. So, there are various such applications are there. I was involved in one of the projects in which there was a mineralization. So, one economic mineral vein was going, a thick vein was of few meter thick was going through an area. Now, if the government give to lease for exploitation of that mineral, then they have to give some extra area so that the mining can be done. Now, so that means simple buffer analysis, and after that then whose land will go in that lease, that information, if we want to extract that information, then we need to have a revenue record. Now, here the example I am just taking is involving only 2 layers, but sometimes in our proximity analysis there can be more than 2 layers and still we can perform such analysis. The only thing, our rules or constraints can become little complicated as compared to just having 2 layers. Now, in this proximity analysis we can also do mapping which is called accessibility mapping, and that accessibility mapping basically it is also connectivity function, under connectivity function. So, the rules what are being put here, for example, that road, if by road it has to be travelled, now time is coming here. So, then 2 km per hour, and if one has to travel through fields not by road, then the the distance it will cover 1 km per hour. So, it is just half, and if one has to pass through the bushes, then this would be 0.7 km per hour. And of course, the swamp and rivers inaccessible, that nobody will go and swim through that. So, an unit of measurement in our analysis of accessibility mapping is time. Now, let us take example. Here there is a well, a groundwater well, and what we are having a land use map where we are having the swamp, where we are having fields, because fields the travel time is 1 km per hour. Then we are having information about the swamp, and we said these are inaccessible, so nobody will travel through. We are having then a river network, a stream network and road network. So, this is just to make clear that this is the river and the rest are the polylines are roads. Now, if for this location I want to know that I want to prepare a accessibility map, that how much time it would take to fetch water from that well. So, here we are getting now these buffers are being created, not circular buffers, more realistic buffers where these conditions are there, these constraints have been put. So, like here what we are seeing that if close to this place, then 30 minutes it will take only 30 minutes to reach to the well and fetch the water. Whereas, if one is located on this area in the second sort of polygon just outside the 30 minute, then it would take 60 minute, and then finally the outermost buffer is showing that it will take 90 minutes. So, because we have constrained that the swamp and rivers are inaccessible, so therefore, we do not see any accessibility here. So, likewise a lot of things can be planned before anything really happens on the ground, or a lot of things can be analyzed to provide certain benefits to the community by this. So, if a person who is here, say for example, then he has to spend 90 minutes time if it is possible, and if it is possible, then a new well can be created, a new hand pump can be installed, so that the people, those who are living, will fetch the water in only few minutes, not in an hour. So, likewise we can do these accessibility mapping involving connectivity functions, overall connectivity functions, under which we are discussing proximity and accessibility. Now, a spread function is having lot of applications, especially in flooding or reservoirs planning and other things. So what a spread function does basically, again it evaluates the phenomena that we are trying to spread, maybe water or oil, natural oil, dilute or accumulate with distance. So here we will be putting then other conditions also, that the distance can be expressed in unit of length, travel time or cost also. That can be calculated, no issue. So the distance either unit of length, that is travel time also, and the cost form. Now spread functions have characteristics of proximity and network function. So it is a mix up of these two functions, a hybrid kind of function, where the proximity is also maintained, because things have to be connected. In case of say flooding, a lower ground may be having water, but in between we are having a ridge, and then on the other side we are having a much lower ground, but since it is not connected, water cannot reach to that place. So there has to be a connectivity and proximity, and of course network is also there. So that we will see. And the spread function basically evaluate phenomena that accumulate with distance. And what is there? What are other things? That these are used to calculate transportation time or cost over a complex surface. So because many times, especially like in mining, you might have seen some open cast mining, where these are not underground but open to sky, so they are called open cast mining. As we know that as mine gets deeper and deeper, it involves more time and ultimately more cost. Whereas when mine is shallow, only the travel time reduces, or travel time is less, and therefore cost is less. So basically what it is accumulating? It is accumulating the time, travel time, to fetch a mineral or ore or coal from that place or deeper from the mine, and then ultimately it cost. Not only time, but it cost in terms of money also, because the material has to be transported. Say a mine is already 100 meter deep now, so that much is there. Initially it was on surface or near surface 10 meter, so the cost was nothing, and the production was very high. So if we want to maintain the same production as we did, as we want having in initial stages, that means we have to put extra cost by putting extra trucks, dumpers or many such features. Then only we can maintain the same output, otherwise output will also reduce. So the same thing is also, this spread function can also be utilized in even in case of underground mines. As mine gets deeper and deeper, the travel time increases and cost. So this estimation of the time taken to walk in a relatively rugged terrain, this example I have given, that the more you walk, the longer it takes to walk over the similar terrain. That the first 5 kilometers you may walk in 1 hour, the first hour, and then next 5 kilometers you may take 1.5 hours, and maybe next 5 kilometers you may take 2 hours. So because your tiredness is getting accumulated. It is a spread function, and dispersion is just opposite of spread function. So it is a concept wise it is almost same. Now this is a consequence of cumulative efforts over time, as we know. So if there is a topographic relief or undulated terrain, then because this incline or anything which impedes the movements. So if I have to go uphill, it will take more time, but while going downward it will take less time. So while doing this while doing such estimations, we have to take care about this, that a topographic incline impedes movements, and differently in case of uphill, downhill or across slope. So in a good planning, even in case of mining or road construction or for many other transportation purposes, these things can be planned, these things can be estimated or modeled before really anything happens on the ground while employing such functions. So a spread function is also applicable for various other things like estimation of output as mine gets deeper and wider, the output reduces. This example I have just given. Then pollutants plume in air, surface and subsurface. As distance, more travel that pollutants will do to cover the distance, it will disperse, the concentration will reduce. It is a reverse, but the same way. Now, other examples are the determination of inundated area due to dam construction. This is a very much requirement, and nowadays like in India, a lot of small size dams or recharge structures are created or check dams are created for groundwater recharge. And all these things, before really anything happens, we can model not only the location, but the height of that dam and how it will, once it comes on the ground, how it will inundate the area, how much area it will get inundated. And if you can have a land use map and revenue records map also, then you can know that which type of land will be inundated or whose land will be inundated. So, that much modeling can be done before really anything happens on the ground. And as I promised that I will be also showing a beautiful demonstration of dam, how dam can be simulated, DAM, not DEM, dam can be simulated, reservoir can be simulated on computer or can be modeled. Now, determination of flooded area due to dike burst, sometimes there are embankments, dikes. So, if anything happens, how the flooding will occur, that can also be modeled through this tool. Then spreading of pollution, dispersion, and the construction of canal is related to accumulation of cost. So, we know that with every meter by which the construction of canal proceeds, cost accumulates, because it is now more travelling is involved. And this is about the dam construction. So, first I am showing through a schematic, and then during later on through demonstration I would be showing how to simulate or how to model on the GIS software. Here there is in the background what you are seeing contours, but we will be basically we are using the digital elevation model, but for simplicity it is shown, the terrain is shown through topographic contours. What are the conditions? That water level is plus means above this. So, 290 meter above mean sea level. So, that is why plus is there. Now, total volume is, you may set the target, or while modeling you may get that calculation also, and the total area, the inundated area in the upstream. So, suppose a river is flowing like this. Now, a dam is constructed, this is the dam axis, and having this height of 290 meter, then how that area will get inundated in the upstream. Now, it is, since it is being done on computers on a GIS platform, so we can create various scenarios for making better decisions by decision makers. So, instead of, if I just increase by 5 meter the height of the dam, like here, the location remains same here, the height has increased, immediately you would find that the area has increased tremendously and also the volume has increased. So, if this first option is not providing sufficient water, say for irrigation or for groundwater recharge, then we can drop that idea and we can work on this idea that I want this much of water. Now, immediately you would know that how much area will get inundated in upstream. Now, next question for decision makers is whose land is going to be inundated, or which type of land use is going to be inundated, whether it is a reserve forest, is a agricultural land or wasteland or any other type of land use. So, if it is agricultural land, then whose farms or whose agricultural lands will be inundated, that can be found out very easily by involving a revenue record map. In India, in northern India, it is called Khasra map. So, if we involve that map, immediately I would know whose land will be inundated. And for compensation purposes or for other environmental clearances or other such processes, such information can be very useful. And remember, nothing has happened yet on the ground, everything in the planning stage, and various models various scenarios have been generated so that the decision makers can take the most judicious and appropriate decision. Similarly, for in case of flooding, like here this example is the real example for Bangladesh, and because we know that the Bangladesh most of the land of Bangladesh is not having much height from above mean sea level. So, it is just say 2.35 meter. Now, the area with elevation below 2.5 meter and connected, because overall recall this is connectivity function, and if dike fails, then which are the areas, this is the failure of dike. So, which are the areas will get flooded, these are the areas. Why other areas will not get flooded? Because they are not connected. Like here in a crude way of doing analysis, then because here we said any ground less than 2.35 meter, so as a flooded area. But this kind of estimation or mapping is completely wrong, because different areas are not connected. They do, though they are having, different areas are having lower grounds, but in between there are higher grounds. So, for a more realistic analysis of this spread function or flooding, we need to know where exactly the failure or a scenario, and which are the only the areas which are connected with dike failure, then they will be flooded. And once you have got this, because in the background you are having a digital elevation model, so definitely you can calculate the area and also the volume of water. And now if this water has to flow, then also you can bring the discharge and other things, and if you know the velocity, you can also calculate how much time it will take to come out that of flooding situation. So, all these things, once one more realistic scenario has been presented, then further analysis can be done. And this is here I would like to bring a very important point here, is that from a GIS user or a specialist point of view, more you deliver, more you are asked to deliver. I am repeating, more you deliver, more you are asked to deliver, because you have given some very realistic, say in this one, an example that I have for your higher ups, you say, sir, this is the best scenario which I am going to present to you, that only these areas will get inundated. Not this does not mean that any area which is lower than this area will get inundated, because it is not connected. So, your higher ups would be very happy that yes, you have presented a very good realistic scenario. Next question he would say, can you calculate how much area will get affected? Can you calculate how much water will be involved there for this inundation? So, that can be done very easily in GIS. Now, once you have done, then he may say, can you calculate that how much time it would take to drain out this water, and what would be the the speed of the water or velocity of water from that area. So, more you deliver, more you ask to deliver. Now, this do not take in the bad sense. It means that when we are asked to deliver more, we work more, we develop new tools in GIS, and this compulsion has really allowed us to develop GIS further and further, and it is making inroads in all real problems, ground related problems in the world. Whether it is related with pollution, it is related with mining, it is related with civil engineering, road construction, dam construction, everywhere, or in natural disasters, almost every domain of our life, GIS can play some role to large extent. Now, the last one before I close, that this seek or stream functions, as I have said, that more full length discussion we will have when we will be discussing surface hydrologic modeling using a digital elevation model. But anyway, before that, the seek functions basically determine optimum pathways using one or more specified decision rules. So, rules have to be there. The process is repeated till one or more decisions rules becomes inapplicable. And examples are determination of path for water flow. So, using a digital elevation model, that means one can determine even a drainage network, and sometimes very accurate drainage network or stream network you can do it. Once the stream network is there, then a person who works in hydrology will ask, can you develop a stream ordering, which are the first order stream, second order, third order, based on two very popular schemes. One is Stellar and Shreve, and you say yes, I can do it. So, once you do that one, then they can say, can you identify the individual water sets? Of course, you would say yes, I can do it. So, more you deliver, more you are asked to deliver, and as you keep delivering, people will keep asking and they will compel you to develop more and more your expertise as well as more GIS subject itself. In highway planning also, these seek functions can be used to large extent, and also like example is given here, that this is my these are my starting points over my terrain, which is shown in form of contours, and automated flow path generations can be done. So, if there is a pollution source, point source pollution, now I would know exactly how it will travel through these streams and how it will get dispersed. And dispersed, if that information, that knowledge is available, that too can be modeled here. So, using simple contour maps, I can develop flow paths as well using this seek functions. So, to that extent it is very, very useful. So, this brings to the end of this discussion. After this, we will be having a demonstration on software. Thank you very much.